I think we have a quorum, more or less. On Tuesday, we're going to devote the class to the projects. So the goal on Tuesday is actually going to be to talk a little bit about each of the suggested projects that are on the website, which you've probably looked at. You're not constrained to those. You can come up with your own project ideas. I reiterate that I recommended rather than forming teams with your best buddies who have taken all the same classes that you have, it's better to try to find people who have taken classes you haven't. The best projects tend to come from teams that have a breadth of skills, because it's easier to divide the labor. And team sizes can be 2 to 4, basically. That's the range. If you need help forming a team, let us know. That we're happy to help with some matchmaking. If you have a particular idea but don't have a team, feel free to float that idea, and we'll see if we can form a team around it. So you're expected to have your team formed and a project proposal by March 8th, which is a week from Tuesday. Okay, so on that Tuesday, a week from Tuesday, we'll devote part of the class to having each team get up and say a few words about what they think they're going to do. Okay, this coming Tuesday, in addition to talking about the projects, we're going to talk about project management. So how you should structure going about accomplishing the project. The projects are done in a pretty incredibly short period of time. There's not a lot of time, so you have to be pretty well organized to get things done. The other thing that we're going to do is also tell you a bit about the toys that we have available. We've got quite a few toys that you can use in your projects, and so it might help to inspire some ideas to know what those toys are. They range from bigger, fancier robots than the ones that you're using for in the lab now, a variety of different boards, kits for assembling robots, the lab localization infrastructure, which uses infrared reflectors, a few other things, but we'll tell you about them on Tuesday. Okay, so today I'm going to finish the discussion of threads and then talk a bit about scheduling. And the context in the lab, the context in which this is relevant is if you're running code on the PowerPC under VxWorks, or, anytime you're running code under an operating system, if you're doing embedded coding, you're probably using threads in one form or another. Even if you're running without an operating system, you're using a lot of the principles of threads if you do any interrupt-driven I/O. So I'm going to go through an example, which is an implementation of a very common pattern called the observer pattern. The scenario that I presented to you is, you've got a sensor somewhere that detects whether the engine of an aircraft is on fire. And you've got possibly a distributed system, or possibly just tasks within a coherent system that are observing data from this sensor. So the flight computer, for example, will switch to a mode where it doesn't pump fuel to an engine that is on fire. And the process that handles the display, the cockpit display, will, flash lights and sound alarms and all that if the engine's on fire. Okay, so these are two tasks observing the same data. That data, and there's presumably a third task that is just handling the I/O from the sensor and updating the state of the system. So you've got a little state machine that says, engine's on fire, engine's not on fire. That gets updated by this task that is observing the sensor data, right? So this is a very common scenario. In fact, this observer pattern is quite universally used in user interface design for embedded systems. Okay, whatever gets displayed to the user is updated according to this observer pattern. So it's a very common thing to be doing. So here's a C program that implements kind of a template, and we'll go through the details of this program. And I want you to help find problems with the design. Okay, that's what we're going to do. So we have some value. In this case, it's an integer in statically allocated memory. So this is outside of any procedure definition. So this is a static global variable in a C program. We then have a procedure that will notify any registered listeners when this value changes. Okay, so this is actually just a type definition for the notify procedure. So if you're charged with writing the code that handles the cockpit display, for example, then you would create a procedure that implements this type. So it takes an integer argument and returns a void star. Okay, and then once you've created that procedure, you would call this add listener method to register your procedure. Right, and so what you're doing is you're telling the system that you want to be notified whenever this integer changes value, so that you can update the cockpit display. Okay, it's a nice modular design that way, right? You don't have to worry about how the integer gets updated. You don't have to worry about what other tasks around are also using that integer value. You just worry about your problem, which is updating the cockpit display. So presumably the body of your notify procedure would take the new value of the integer, whatever it is, and update the display accordingly. Now, because we have to keep track of the listeners, so there might be any number of listeners, so we need a list of listeners of some sort. So one way to do that would be using a linked list. And so a linked list could be structured like this, where you have an element in the linked list, which we'll explain what needs to be in that element, a type for that element, a pointer to the head of the list, a pointer to the tail of the list, and we initialize these to null, which we will interpret as meaning that there's no listeners registered. Okay? So when the head and the tail are both null, there's no listeners registered. Now, whatever procedure is monitoring the sensors, for example, and updating the integer, would update the integer by calling this update method. Okay, and it's this update method that's going to have to take care of notifying all registered listeners. Okay, so let's go through in a little bit more detail. So what is the linked list of listeners going to look like? Well, it's going to be a list of objects, which are in C are structs, okay? And each struct has a pointer to a notify procedure and a pointer to the next element in the list. So it's a standard way of writing a linked list, all right? So that's pretty straightforward. Now, so when you want to add a listener to the list, you could provide an implementation that looks like this. You have an add listener method that takes as an argument a reference to a procedure. If the list is empty, then you do something slightly different than if there's already things on the list. It's only slightly different, right? So if the list is empty, you allocate on the heap some memory for some particular element type. By the way, we're in an embedded systems context. Okay, this is a aircraft flight control system, safety critical. What do you think about this malloc call? Does everybody know what malloc does? Does anybody not know what malloc does? Let me. Don't be shy. If you want me to explain it, I'm happy to explain it. Okay. So in if you remember the memory map, okay, you've got some region of data memory. You have the stack pointer, which typically points to the end of that region, and the stack will move up and down as you call procedures. Your static variables get allocated at the other end, and then typically you will define some region also with a flexible boundary, okay, which is called the heap. And this, when a piece of your program needs a place to store something temporarily, it calls malloc, which will simply allocate a chunk of data in here, okay, and then return a pointer to that location. So malloc returns a pointer to memory that you can use. And in this case, you need to tell it how much memory you want. So you use the size of procedure to tell it how many bytes you need. It returns a pointer. You can fill it with your data. You then should call free when you're done with it. Okay? So after you're done using this memory, you call free, which will then deallocate that, enabling it to be reallocated later by another call to malloc. Now, there's a number of problems that can occur in an embedded system with a heap. There's no eraser here. I guess there's always fingers. Sorry? Oh, okay. Thank you. I apologize to those of you who are relying on the screen capture. This is not being screen captured, but you know, there are advantages to coming to class and live presentations. Last Tuesday's class, the last 2/3 have no audio because the battery went dead. So I recommend not counting on the screen capture. Anyway, what can happen when you're doing a lot of malloc and free, well, first of all, there's a number of problems. One is you could malloc memory, enough memory that you overlap with the stack. Disaster when that happens, okay? Because that means if you overlap with the stack, you could return from a procedure to some arbitrary location, which might be, you know, a pointer to a, you know, the end of a linked list. And now you start executing code, whatever's in that linked list, right? So that's really bad. So you have to worry about how much memory you allocate using malloc, okay? The other thing is that over time, the memory on the heap can get fragmented, okay? So you allocate a chunk of memory, then you allocate another chunk, then you allocate another chunk, then you free this chunk, okay? So now you have a hole, and you can reallocate that if you happen to call malloc again with something that requires exactly this number of bytes or fewer bytes, you can reallocate it. But over time, you could end up with a kind of Swiss cheese of memory with a bunch of stuff allocated and a bunch of holes that are too small to use. By the way, this is probably the primary reason why you end up having to reboot your machine periodically, right? Because you need to kind of throw everything out and start with a clean slate. Now, one technique which is implemented, for example, in Java is to do garbage collection, okay? Which is basically you go through and you find all the allocated chunks of memory for which there is no live pointer to them anymore. So pointer's gone out of scope. It was on the stack. The stack pointer has moved off of it, and so it's no longer live, okay? At that point, you identify that it can be freed, and then you can, in addition, move things around in here to defragment the memory. One key problem with that is that during the time that you're defragmenting the memory, you cannot reference any of the variables on the heap because they're being moved around. Your heap is in an inconsistent state. So the straightforward garbage collection techniques are what are called stop the world techniques. You simply stop the program, interrupt it, okay? Nothing in the program runs. You do all your garbage collection, determining which pointers are live, which ones are not, and defragmenting the allocated memory, and then you resume your program. That can create pretty sizable pause times, okay? In Java, on a machine like this, I've measured 1/3 of a second. It just stops, spends 1/3 of a second reallocating memory, then resumes the Java program. There's not a lot of embedded systems that can tolerate a pause time of 1/3 of a second, right? It's pretty rare. So that kind of technique is really problematic. People have developed much more sophisticated garbage collection techniques. In fact, there's a whole research area around bounded pause time garbage collection techniques. And they can get, it's fairly routine these days with specialized Java virtual machines to get the pause times down to about a millisecond. A millisecond is still a tremendously long time for many embedded systems. Okay? There's not a lot of embedded systems that can tolerate a millisecond pause time. You miss sensor data, you can't respond to interrupts, you can't do anything, okay, for a millisecond. That's a lot of time. So Java is not actually that useful in a lot of embedded systems because of this garbage collection issue. Yeah, question?
I'm just curious, what's like the embedded system or why milliseconds won't kill you?
Well, it really does depend on the embedded system, of course. I mean, if it's a microwave oven and it's just doing the user interface, anything that is user-focused, human interaction-focused, can tolerate things down to tens of milliseconds are fine, right? Humans don't notice latencies lower than about 30 milliseconds. Okay, but if it's interacting with devices, often those devices have very time-critical actions. Right? You need to respond to things. Text from my daughter. You need to respond to things, promptly. So it really does depend on the application. You need to characterize what your application needs, and you need to understand what the software infrastructure can deliver. Yeah, question? No, not necessarily. The defragmentation doesn't necessarily occur every time you do garbage collection. It depends on it. Yes, you have to update all the pointers to the variables too. So when you implement a Java virtual machine, there's a lot of bookkeeping. You have to keep track of not only what's allocated on the heap, but where all the pointers to it are. Okay, and you have to be able to update those pointers. That's very different from C, where malloc just returns, if it's a 32-bit machine, it returns a 32-bit number. And there's no way to tell what you can do with that number. You can do arithmetic on that number and then use that result as a pointer. Okay? C really gives you control over the memory, which is, of course, dangerous. Yeah? Yeah, so malloc will typically, a typical implementation of malloc will disable interrupts so that it becomes atomic. So for example, there won't be any, if there's a thread library, there won't be any context switching during a call to malloc. That means, of course, that you need to, when you implement malloc, you need to make it quick, right? So for example, you wouldn't want to do defragmentation on a call to malloc. That would be risky. Okay. So these are issues that come up, but let's think about this particular context. We're designing an aircraft system. How safe do you think it is to use the heap for this? Should we have instead just used a static variable? Maybe so, right? Maybe it would have made more sense. We know that there's only one user interface process. We know that it's going to want to listen to this sensor. Just allocate a static variable for this thing. Yeah?
What if you have everybody register their...
Right. Yeah, so the observation is that if you have all of your listeners do their registering at the start of the program, and you know that there's a finite number of those listeners, and you know how many they are, then using malloc is fine, right? You're going to allocate a bunch of memory. It's going to be contiguous. It's not going to fragment the memory. You're not going to free it ever. But then it functions equivalently to a static variable, so you might as well have used a static variable. Yeah.
In this program, you don't actually check to see if actually malloc is.
That's another very good point. This code is not written in a very safe way because, in fact, a typical implementation of malloc will prevent you from encroaching on the stack by, checking whether there's free variables, whether there's free memory below the stack pointer. And if there is no available memory, it'll return null. So you should check for that. Yeah.
I have a question about malloc. Isn't it usually defines a system call?
Uh,
Or is it usually called system call with an EOS manager memory?
it is. So malloc is typically part of the implementation of an OS, but one of the things we're going to look at, starting later today is what people call microkernels, which are basically really stripped down operating systems, right? And they are often just a bunch of procedures that maybe implement the pthreads library, implement malloc, implement the free. And is it really an OS? Well, not really, but yeah. So, an operating system is a collection of services. And this is one of them. But you can also use those services in an a la carte way. Right? So anyway, this particular implementation here is kind of iffy because it's using malloc, not checking the result. Should have probably used a static variable, but these are things to think about. Okay, so the way it works is if the list is empty, you create a chunk of memory to store the element that you want to put in the list, and then you put it in the list by just having the first element. Let's see. So, yeah, right. So this the listener element of the data structure, the element type data structure, points to the procedure that was specified when you called add listener. Okay, and next points to null, meaning that this is the last element on the list. That's how we'll interpret that. Okay, and the tail of the list points to the head of the list because there's only one element on the list. The reason for maintaining both a tail and a head pointer is that it's more efficient to access both ends of the list if you have both pointers, right? If you only have one pointer, you can still get all the information. If you have the head pointer only, you can get all the information, but you may have to traverse the list to find the last element. So the else loop is if there's already something on the list, then again we allocate some memory, stick it on the end of the list by just using the tail pointer, update its next field, then set the what is this? Oh. Yeah, this is probably null, right? By definition, it's the tail of the list. So the next pointer should be null. Yeah?
Isn't it tried, like we add one element to the next, so we malloc like space for the next, and then we are moving.
Right. Oh, yeah, that's right. Of course, that's what we're doing. Yeah. So we allocate an element which contains. This has two objects in it. It has a pointer to the listener, and it has a pointer to next. So we malloc that. So we have a pointer to that location. We call that the new tail. Okay, because it's the new end of the list. And the previous tail, we update its pointer to the next element, which was presumably null. We change it so it's no longer null. It points to the memory we just malloced. Okay, and then we set the variables of this data structure. Okay, so that's a sort of standard linked list operation. But all right, so if the procedure this procedure might be called by an interrupt service routine. So for example, you have a temperature sensor in the engine. When the temperature exceeds a threshold, it decides to request an interrupt. The interrupt service routine calls update to provide a new value for the temperature. Okay? And the update procedure assigns the value and then notifies the listeners. Okay? Now, you could construct a model of this update procedure. So you've seen state machine models, and it's sometimes pretty useful to construct state machine models of programs. In fact, a lot of static analysis tools that systematically explore behaviors of programs in order to, prove certain safety properties. So, for example, you might be able to prove that even though you're using malloc, you use it in such a way that it will never run out of memory. Okay? In order to do that, systematically, you could construct a state machine model of the program. The state machine model of the program could be able to prove that malloc is called a finite number of times and construct a bound on the number of times it's called. Okay? And then, that would give you confidence that you're not going to run into problems with running out of memory. All right? So a state machine model for this update procedure might look something like this. Recall that, I'm assuming that this is going to be invoked, say, by an interrupt service routine. Right? So I'm thinking of this state machine as a process or a thread. And when it's not running, it's just idle. Then when it's invoked, there's some trigger, which I'm calling arg, that indicates that this is called. And then this new x, which is on the stack, gets assigned the argument that is passed in. Okay, so I'm kind of showing some of what the compiler does. The compiler takes the argument to this procedure, puts it on the stack. So, and that's going to be this new x variable, which is on the stack. In addition, the x variable is on the stack. So it assigns x to new x. And, x is not on the stack. X is, sorry about that. The notation is slightly different here. This is from the textbook. Value in the textbook is replaced by x. So x is the static global variable that stores the value. Okay? So that gets assigned the new value. Then to notify the listeners, we take an unconditional transition where we set element to head. That's this. Element variable gets assigned the value head, which is a static global variable. And then this state has essentially models the conditional branch. Okay? If the head is 0, there's nobody to notify. So we just go back to idle. If the element is non-zero, we take this transition, and then we unconditionally take this transition, which calls the listener procedure. So this line right here is calling the listener procedure with the argument new x. Does everybody see how this line works? This is kind of a bizarre thing about C, but we dereference the pointer to the procedure. Okay? That's what the star is, dereferencing a pointer, and then calling the procedure with this argument new x. Okay? It's a very common thing to do in C. And then it updates element to point to the next item in the list, and then we return to this state. And again, if that was the last element, we go to idle. Otherwise, we go back and notify the next listener. So we could go around this loop as many times as there are listeners, notifying each listener, and then eventually returning to idle. Okay? Now, so I've given you a program. It's reasonably complete. Okay? We would have to make this really complete, you'd have to write the notify procedure that updates the user interface display, and you'd have to write the interrupt service routine that handles the sensor data, but you can imagine how to do that. So we've got a structure for a program. Now, the question is, this is in fact probably going to be a multi-threaded program, because I've already talked about how the sensor is going to request an interrupt, so the interrupt is going to occur at an arbitrary time, and it's going to kick in interrupting whatever was running. So will this structure work? in the context of multi-threading. What are the possible problems that could occur? Let's look at this update procedure. Well, let's look at this add listener procedure. Suppose you're in the middle of calling add listener, an interrupt request comes in, and update gets called. What's going to happen? Yeah, you could get real chaos, right, if that happens. Why? Well, here we're actually changing the structure of the linked list. But in this other procedure, we're iterating through the linked list. Okay? So what could happen is, say we're, at the state where, let's see, what could be, it's very difficult to reason, by the way, about what kind of problems could occur. Okay? But you have to think about every operation being actually something that occurs in several steps. Let's assume malloc is atomic. So interrupts are disabled while malloc occurs, so at least we're not going to get a corrupted heap. Okay? But once malloc occurs and this tail, the next variable of tail has been updated, okay, we could have an interrupt occur before we update this global variable tail. Okay? Or it could occur after we update the global variable tail, but before we fill in the data structure. Okay? So in particular, suppose that the interrupt occurs right here. Okay? And we start executing this procedure, iterating through the loop. What do you think is going to happen? You might get an infinite loop here, right? You might get this while loop may not terminate, and actually it's much worse, because what's going to happen, notice if we get the interrupt right here, what is the contents of the next field of the last element of the list at this point in time? Random data, whatever was in memory, right? Whatever was previously freed, okay, that got malloced, that's what's in this next pointer, okay? So the next pointer of the last element of the list points to some random place in memory. This procedure, this procedure is going to go to that random place in memory, read the first 32 bits of that random place, and call a procedure at that address. What's at that address? Random data. Data is program. Who knows what code you're executing, right? I mean, that data, whatever's at that location, is going to be interpreted as instructions, and it's going to start, doing whatever those instructions say to do, which could be anything. Complete chaos, right? Does everybody see how bad this could be? This would be, extremely difficult to recover from. This is reboot time. Now, how likely is it to happen? Well, the sad part is, actually, it's not that likely, right? I mean, you'd have to, you can get away with very sloppy programming because you're going to test this on the bench. Maybe if you're really doing rigorous testing, you're going to test it a few thousand times. What are the odds that the interrupt will occur before this update occurs? Well, probably pretty small. So it's going to work fine in testing. It's going to fail when it's in the airplane, okay? Because it's used for many more than a few thousand times. So testing is not a good way to determine whether programs work when you're doing multi-threading. In fact, testing is really almost useless, okay, for giving you confidence about programs in a multi-threaded context. Okay. So, all right, so what should we do? Well, we need to put some protection mechanisms. We need to make certain operations atomic. So if we have a POSIX thread library implementation, that's pretty easy to do. We can use a mutual exclusion lock. And the way that works is pretty simple. Again, I want to emphasize this is a service that is typically bundled with an operating system. But you can get a pthreads library that runs without an operating system, okay, for many platforms. And in fact, that's commonly done with embedded systems. You just get a pthreads library, get it working on an embedded platform without an OS, right? So the pthreads library has a data structure that it calls a mutex, okay, for mutual exclusion. So in this case, we've declared a static variable called lock that has this mutex type. So it's just a data structure. And you call, if you call pthread mutex lock and pass the address of that lock, what this does is that this procedure will not return as long as there is any other thread that holds that lock. Okay, it will return only if it can guarantee that you now exclusively own that lock. Okay, so when pthread mutex lock returns, you know that this body of code, which also tried to access the lock, is not executing. And vice versa, when this code is executing, you know that this body of code is not executing. They cannot, the code between the pthread lock and unlock, two chunks of code cannot be simultaneously executing. All right? Implementing this procedure, mutex lock, is very tricky. All right? It requires an indivisible test and set. It actually requires hardware support in the processor. Okay? You can't implement it by reading a memory location, seeing if it's true, and then if it isn't, then making it true, because an interrupt could occur between the time you read the memory location and the time you update it. Okay? So you have to be able to read and update in an atomic step without an interrupt occurring, which requires hardware support. Okay, so yeah, so that seems good, but this carries a significant risk. Right? In particular, there's a risk of deadlock with this implementation. So in particular, suppose that, so right here on this line, okay, we call an arbitrary procedure, a notify procedure, that is provided by a client. So, you know, often this code is developed in teams. So the guy doing the user interface design implements this notify procedure, and you know, some other guy is implementing the flight control software and so on. So when you design this code, you don't really know what this procedure is going to do, and you need to guard against all the possibilities. You figure it could do anything, right? Well, suppose that this procedure itself needs to acquire a lock. That would be common, for example, if it is, so suppose it's updating a cockpit display. There's probably lots of clients updating the cockpit display, so it needs to acquire a lock to update the cockpit display. So this procedure could, in fact, stall trying to acquire a lock and not return. During the time that it is stalled, of course, we hold this lock. Suppose now that the code that holds the lock that this procedure is trying to acquire decides to call add listener. Then what will happen is that code, the code that is blocked here trying to acquire a lock, will be permanently blocked, and the code that calls add listener will be permanently blocked because the update procedure is holding the lock. There's no way out of this except a reboot. Okay, you got to restart the program because these two threads cannot continue. So this isn't a great design. So how could we make a more robust design, something that is a little safer? Yeah.
Can we free it before we call that, like,
Yeah, so that's the right intuition. We'd like to unlock this before iterating through this list, but we can't just move this up here. Why not? Right, because then, I mean, you're iterating through a data structure that could be modified while you're iterating through it, right? Yeah.
You should make all of the shared data adjudicated by.
Yeah, you could do that. I think a simpler way to say that is you should just use a single lock, right? If you
That's one way to do it, but the problem with locks is that once you introduce them into a design, you have to guarantee that locks that the other parties in the design can use.
That's right. So it's a very non-modular approach to use a single lock, and it's very inflexible. It requires a fairly draconian design. It is sometimes what people do. So for example, if any of you have used TinyOS, it has a very nice property that it's provably deadlock free. TinyOS applications don't deadlock, and the reason is that everything is implemented using a single lock. And in fact, the single lock is the interrupt enable state. So you actually use interrupt enable as your lock data structure in TinyOS. But it's a very inflexible technique, and it doesn't scale very well to big systems. So you'd like to have a design that allows the use of multiple locks. So what other ideas? What else could we do here? So the problem is we'd like to release this lock before we call this procedure, but we can't iterate through this data structure after releasing the lock safely. Yeah.
So why don't we just like release the lock after the while and then lock it again before the element is equal to element next? Unlock when we are running that function.
I see.
Lock it again for the next loop comes back.
So unlock it right here, call the procedure,
Then lock it
and then relock it before. But the problem is that element now may point to something that actually, you know, that might work as long as we don't also have a remove listener procedure. Right? But if we have a remove listener procedure, that's not going to work because when we reacquire the lock, element may no longer be on the list. Right? But notice that very tricky reasoning, right? If our list can only grow, then it might be safe to do that, right? But how do you know, thinking through that that's really safe is actually very difficult. It's really tricky. It's easy to get it wrong. So I don't like that solution. Other ideas? I want to emphasize that this is a very common design pattern. It's hard to build any interesting system that doesn't use this design pattern. Yeah.
How about adding another lock, different lock for that part? So if you're adding or removing, you use the second lock. The first lock is just like so first lock is for adding, the second lock is for removing, and then you put it around the whole while. While we're running the while loop. But I mean, we can add with the condition that I said before.
That might work. Gives me a headache thinking about it, but it might work. Yeah, Bailey. That's a good idea. I like that one. So let's do that. That was my solution. Okay. While you hold the lock, copy the list. Okay, the whole list. Just make a copy of it. But nobody else can see that copy because it's on the stack in this update procedure. Right? So there's no other references to that copy anywhere in the system. So then we release the lock after we've made a copy, and then we iterate through the copy, calling the procedure. So now there is kind of a race condition here because a procedure could call add listener, and that listener might not get notified right away. But that may be okay, right? I mean, there may be some asynchrony here, but you have to think through whether that's okay, right? But if, is it okay for a listener to be added to the list and not get notified until sometime after it was added? Okay. But this code has a worse problem. Okay, worse than deadlock. It's what we call an insidious bug. Okay, it's a bug that may never be actually observable or measurable, but could be disastrous. What is it? Yeah.
Is it possible that we call multiple files on the updates and just add memory, and then run out of memory? So because you're making copy, right?
Yeah.
Every time you make a copy, you get more memory.
That's right. So each time update gets called, we're going to pay a price in stack memory. But let's assume that update is called a bounded number of times, okay? But it may be called multiple times, right? And it may be called multiple times by separate interrupt requests, right? There might be multiple sensors updating this data, for example. Yeah.
I think the copy method is just sort of us stumbling into the fact. Unreliable way to prevent that from happening is to decouple.
I'm not sure I understand the proposal.
So, for instance, if instead update you try to update values using a callback method like we're seeing here, if they were, let's say, pushed onto a queue,
Oh,
was processed asynchronously.
yes.
You have the deadlock problem because you have not.
Right. So the suggestion is actually to completely change the architecture so that rather than calling a callback method, which is what this notify procedure is, instead you could, when you do the update, you stick something in a queue, and then you separately pull stuff from the queue. That's actually an excellent suggestion, and in fact, that is my preferred solution for this. I would do this in a very structured way using what I would call a concurrent model of computation. For example, a data flow model. So in a data flow model, in LabVIEW, right, you would have a box with an output that is telling you the sensor data, and all the listeners would merely be destinations for that data, right? This can be implemented quite easily without these kind of deadlock risks and update problems, right? And so understanding how to do something using a data flow style can be a really nice solution to this problem. But we're kind of working at a level lower than that. We're working at the threads level, and this is, unfortunately, it's extremely common for people to do these designs like this using these callback procedures. And this design that we've come up with at this point has a really horrible problem. Yeah.
If you were then updated once you release the law, some other procedure calls update, would it affect, like you're trying to add an element, somebody else calls it?
Well, the update procedure isn't changing the list. So, and each time you call update, you are in a different place in the stack. So they're not going to overwrite each other's memory. But I think your intuition is right, which is, I mean, the problem occurs when there are multiple things calling update, the problem that I'm talking about. Yeah. Yeah. So the problem is that you could have listeners notified of different values. But the problem is even slightly worse. So suppose that update gets called twice. Once it gets called to say, engine's fine, not on fire, and then it gets called to say, engine is on fire, okay? The final state of that variable is that the engine is on fire. But a listener could be notified in the other order. It could be notified that the engine is on fire and then that the engine is fine. So the cockpit display might flash fire and then fine. Okay, now the cockpit display shows that the engine is fine and the engine's actually on fire. Does everyone see how that could happen? Right? I mean, you make a copy of this list. Okay, you're gonna notify. You release the lock. The interrupt occurs. The second update occurs. As a result of that second update, it makes a copy of the list. And suppose that your thread scheduler just happens to go ahead and notify on the second call to update before it returns to the first call to update. That's a perfectly legitimate behavior in this system. So the first call to update is stalled here. The second call to update completes doing all the notifications. Then you return to the first call to update and do your notifications of the stale value. No deadlock. All right. In fact, this problem could occur in testing and you won't see it. Right? Something flashed on the screen. You didn't see that. Okay? This is really bad. And yet, it's extremely common. In fact, every non-trivial multi-threaded program written at this level has bugs like that. I can assert that. Unless it was written by Doug Lea. He's the only guy on the planet that I trust to write code like this. You can't, it just boggles the mind to, think through what could happen here. And yet, this is how people write multi-threaded code. So some people say, well, all right, concurrency is hard. You better leave it to really smart people. Okay? But concurrency is not hard. Humans are very good at reasoning about concurrent processes. In fact, we wouldn't be able to function in the physical world if we couldn't reason about concurrent processes. Right? You couldn't play soccer. You couldn't drive a car. We can reason just fine about concurrent processes. We just can't reason about threads. Okay? Why can't we reason about threads? Well, the issue with threads is very subtle. Threads do not behave anything like the physical world, right? Because what happens is you're proceeding through a sequence of operations, but between any two operations, the state of your universe can change. Blam, at the blink of an eye, right? Without your knowing that it happened, without your being able to observe that time has passed, your state of your universe just changed. It's as if, I'm standing here and all of a sudden you guys are all gone. Right? That doesn't happen in the physical world. So it's no surprise that we can't reason about programs that behave that way, because we have no experience with that style of concurrency. There's nothing about the evolution of the human brain that would make us able to reason about that kind of concurrency, because that kind of concurrency does not exist in the physical world. Right? Is that the only concurrency model? Well, when people say this, they are in effect asserting that that's the only kind of concurrency, but it's not, right? LabVIEW is a concurrent programming language, and it's trivial to reason about issues like this in LabVIEW, right? So it's threads that is the problem, not concurrency. So, all right, I said that. I think, let me just say one more thing and then we'll take a break, okay? The problem here is very fundamental, right? Which is that when we think of the core notion of computation, what computation is, at its very basic roots, is you have a set B of bits, 0, 1, and you have a finite sequence, a set of finite sequences of bits, B star. That's the contents of your memory. Okay? The contents of your memory will be a member of this set. A computation is a function that takes a sequence of bits and gives you a sequence of bits. That's at its root what it is. You can compose computations, and programs specify sequential compositions of these functions. Okay? So each statement in your program changes the state of memory and the state of your registers, which is just taking the sequence of bits and giving us a new sequence of bits. Okay? So function composition is a very clean thing to reason about. The problem is that when you have threads, you know, if you're proceeding in a single thread, modifying the state of your sequence of bits as a sequence of steps, if an intervening thread comes in and changes the sequence of bits that you've been operating on, then you no longer can use function composition to reason about the behavior of the program. So multi-threaded programs are in fact not computations in this sense. They are not functions that map sequences of bits into sequences of bits. What are they? Well, actually, there's kind of no theory for them. So it's not surprising that it becomes hard to analyze, right? We can't model them as function composition. So they're in fact wildly non-deterministic. They're not functions. Functions are deterministic. You give it an argument, you get a result. Okay? Threads are not deterministic because this interleaving can give you a wild non-determinism. And the programmer's job is to prune away the non-determinism. Okay, you put in locks to get rid of the non-determinism. So as an engineering principle, this is a flawed principle, right? You're given a mechanism that's wildly non-deterministic and told to prune it until you get a deterministic behavior. So it's as if I asked you to, design an internal combustion engine by taking a big vat of iron molecules and hydrocarbon molecules all moving around at random and constrain their motion until you've got an internal combustion engine. That's what multi-threaded programming is, okay? You've got this big vat of molecules and you got to constrain their motion until you get the behavior you want. That's stupid, okay? It's a really bad engineering principle. So, all right. So there are ways to improve this, of course. There are things that help. For example, object-oriented programming helps a lot by just hiding regions of memory from pieces of programs, right? You don't want every piece of the program to be able to see all of the memory. That helps a lot, but none of these things are really enough. Okay, so let's take a 3-minute break, and then we'll start talking about scheduling.
Quick question based on this
Okay.
you just demonstrated.
Remind me? Chris, thank you.
So where you wrote simply f is some function that maps some series of bits into some other series of bits.
Mm-hmm.
And the problem, I guess it seems, is that the problem with threads is normally if you have a non-threaded process, you'll have some, like you said, some sequence
Mm-hmm.
and some sequence of n operations on
On your initial
basically,
state.
This is your whole computation, basically.
Right, exactly.
So then the problem with threads is that you have, maybe if you just have two threads, you have F1 and F2, where these are two computations that you want to, basically two functions or whatever you want. The problem with threads is that if you break each one of these up into its constituent atomic operations, then the actual way a threaded process works is a non-deterministic set of all of the permutations of these. So if this is like...
Exactly.
Yeah, so this is I, then the problem is that the some funny threaded product of F2 is something like this terrible thing, which is, I'm just going to use this to say all the possible permutations of
Right. Yeah, so the issue is that ends up not being a function of this form, right?
Well, it seems like it is a function of this form, but you can't determine, because what if you put all of these together, no matter what's happened, you had it. I mean, in the end, you had only one computation actually took place. In the end, you executed some permutation of, you may have had F11 fire, then you had F12 where you may have had an interrupt. Where this is the thread index, and this is like the number of sequential
Right.
operations of the thread.
But the multi-threaded program itself is not specifying a function of
Oh,
this
no,
form.
exactly. But so I'm saying
Right.
the actual behavior of your program is something like this.
Right. So it's even worse because you know on the test bench it looks like it's doing a function.
Yeah.
It's giving you a function,
But
but
each time you actually run the program, it may, in a sense, it'll return a different sequence of these atomic operations.
right.
So, I guess from a theoretical standpoint, you could say, okay, you could actually figure out the behavior of a multi-threaded program by considering all of the possible combinations of these and doing some. But I mean, with anything besides the simple trivial programs, that seems computationally impossible to actually compute
Right.
this.
It becomes intractable. But I mean, people have gotten pretty good at developing formal procedures that can reason through these things, but they do so under some often pretty strong assumptions. Oh, is that what Dai brought these? Okay. So these are homeworks. Yeah.
Okay.
Right. Yeah. So in fact, the way that the formal procedures work is that you construct state machine models of one for each thread. Okay. You have to ensure that your transitions are atomic, which often requires a very detailed modeling of the hardware level.
Extremely complicated.
It's extremely complicated to do. You can't do it on just a C program. You have to know what processor the C program is going to run on. And not just what the ISA is, but what the implementation of the ISA is, right? And then you might be able to tell what all the possible behaviors are.
But even then, the number of possible behaviors may be.
It becomes enormous. It becomes enormous very quickly, yes.
You have a program that doesn't have a fixed number of operations in its execution. It's probably in some very unfriendly kind of an infinite number of possible.
Right, exactly, yeah. Okay, let's start up again. So Dai was kind enough to bring some homeworks by to return. So when we're done with class, maybe you can come up and collect them. All right. So I'm gonna start now talking about one level up from the threads, which is addressing really the scheduling question. So what is the scheduling question? Well, the scheduling question is making a decision about which thread to resume. Now, it's useful to understand the mechanisms, right? Because that's really, I mean, if there's any overall theme in this course, it's about understanding the mechanisms, how things actually work under the hood. And when does an operating system make a decision about which thread to execute next? When is the question even asked? Right? When does the operating system get to say which thread executes next? Is the operating system always running? It's actually kind of a mental model we have of operating systems is that it's always running, but how could it be? If the operating system was always running, your application code would never be running, right? We're talking, single processor, single sequence of instructions now, not multi-core, right? So there have to be times where the operating system isn't running, because otherwise your application code would never run. You have a single program counter, it's executing instructions, it's specifying instructions. If all of those instructions are operating system instructions, your application code never runs. So the operating system is not always running, even despite that being the mental model we have of an operating system. So when does the operating system get to make a scheduling decision? How do you think it works? Yeah.
Would it be like a timer, so we get an interrupt and then go back and run some
Yeah. So that's one mechanism. So what an operating system does is when you boot it up, it sets up a timer, which is an external peripheral, to raise an interrupt request periodically with some period. That period is conventionally called the Jiffy interval. Okay, and it comes from the term, well, I'll get to that in a jiffy, right? The idea is you want it to be small so that, you know, the operating system can give you responsive behavior, right? You know, it tends to, I mean, in Unix-based systems, it's typically anywhere between 10 and 30 millisecond intervals, something like that typically, okay? So a timer interrupt occurs. An interrupt service routine is set up to respond to that timer interrupt. And that interrupt service routine can kick in whenever there's an arbitrary thread executing, right? So how does the operating system, suppose the operating system then, you know, it looks kind of at the state of the world and says, oh, well, that thread's been running for a while. Maybe we should give another thread a chance. How does it do that? Sorry? Yeah, that's at the algorithm level, but I want to talk about the mechanism, right? Your interrupt service routine. What C code should you write to not go back to the thread that was executing when the interrupt occurred, but to go back to some other thread? Yeah. You can set priorities, but that's going to be something you're going to use to decide which thread to execute next. But the question I'm asking is, what's the mechanism for just having decided that you want to execute a thread, then executing that thread?
Can we save the PC somewhere and then change the PC to a different value?
Yeah.
And then when we come back.
So the way that an interrupt works is that the program counter gets, when the interrupt request line is raised, the current program counter gets pushed on the stack, okay? And then any other state, such as the contents of the registers of the machine, also get pushed on the stack, and then the program starts executing the interrupt service routine. So the program counter that you want to return to is on the stack. If you simply return from interrupt, you will restore the registers from the stack, including the program counter, and then resume executing where that program counter was. Okay, but now suppose we don't want to resume executing that thread. We want to resume executing another thread. What should we do? What should the interrupt service routine do? So the picture, here's our memory map, right? Here's our stack pointer when the interrupt occurs. Stack pointer when the interrupt occurs. We push the program counter onto the stack. We push the register values onto the stack. We update the program counter now, which is a register, to point to the interrupt service routine. We start executing the interrupt service routine. If we do a return from interrupt, so now the stack pointer points here, right? If we return from interrupt, we restore the registers, we restore the program counter, and our stack pointer now points here, and we resume executing, okay? But if we don't, but that's going to resume executing at the same thread that just got suspended. So what if we want to resume executing at a different thread? Yeah. We could change the stack pointer. So in fact, a typical implementation of pthreads will actually maintain multiple stacks, one for each thread. Okay? So in a different chunk of memory, you have stack pointer 1. Well, there's still only one stack pointer register, right? But you put another stack logically in memory corresponding to a thread. So when you start up your program, your stack pointer points here, you start executing this code, okay? When you call a pthreads procedure to create a thread, one of the things that does is decide where in memory the base of that thread stack should be, okay? When it starts executing that code, all it has to do is update the stack pointer register to point there, all right? If that thread had been previously suspended, okay, then its stack pointer will be pointing to here, where this is the state of the registers of the machine and the program counter when it last was suspended. Okay? So now your interrupt service routine that responds to these Jiffy interrupts can switch between these two threads at will by just updating one register, the stack pointer. Okay? If it wants to resume executing this thread, it sets the stack pointer to point there. If it wants to resume executing this thread, it sets the stack pointer to there, and it returns from interrupt. When it returns from interrupt, it'll then either get this program counter value or that program counter value. Yeah, question?
How does the memory get allocated in the beginning for multiple threads?
It's tricky.
Be different every time.
Yeah, it could be different every time. So it can be, the implementing, this is where the pthreads becomes challenging to implement well. It's easy to implement poorly. Okay, you just take your available memory and you say, all right, you decide that I'm not going to allow more than 64 threads. You divide up the memory into 64 chunks and you say those are going to be the stacks I'm going to use. But that's not a very good implementation, right? So you could be smarter about it and more dynamic about it. Okay, but threads come and go, so you have to kind of handle it like you do memory allocation on the heap. Okay, and it can be pretty tricky to do, but it's the important thing to understand is the mechanism, which is that an operating system is not something that's magically running all the time. It's actually just some instructions that execute some of the time, for example, in response to a Jiffy interrupt. There's other times when this thread scheduler may be invoked. So typically, anytime you call an operating system service, malloc, for example, malloc will, take a look at a data structure and decide whether to resume executing the thread that called malloc or not. So you could context switch on a call to malloc. You could context switch on a call to printf. Basically, any operating system service, anytime you turn the thread of control over to a procedure that is part of the operating system, that procedure's implementation could invoke the thread scheduler, and so you might not return immediately. Yeah.
How smart is that thread scheduler? Like, does it just randomly jump between different threads? Like,
Oh, it can be arbitrarily smart or arbitrarily dumb. I mean, a simple scheme is round robin. You give every thread a chance to run, and you don't execute it until. But that's what we're going to talk about next. Is how should you decide which thread to execute next? All right. So this, by the way, when you're thinking about these mechanisms, this is where microkernels become what you're really talking about. You may not, in an embedded system, you may not have an operating system, but you may have a lot of these mechanisms anyway. Okay, and you call that a microkernel when you have that. All right, so there's a wonderful book on real-time scheduling by Giorgio Buttazo, which is on reserve if you want to probe into this further. All right, so what are the responsibilities of a microkernel? So the microkernel is, you can think of it as a subset of an operating system. It includes kind of some basic core pieces of functionality, but it doesn't include a Windows system, for example, or a lot of the I/O mechanisms. It may not include a network stack, so you may not have TCP/IP available in a microkernel. But among the services that it would need to provide is scheduling of threads or processes, which means creation or termination of threads, finding chunks of memory to use for the stack for a thread when it's created, recovering that memory when the thread gets destroyed, timing the thread activations and switching between threads, It also provides the mechanisms that implement synchronization, so the locks, mutual exclusion locks, and it can provide mechanisms for input and output. So the interrupt service routines that handle, for example, serial port inputs. There's a bunch of functions that you may have in a microkernel, such as memory management. So if you have threads, you have to have separate stacks, but you may not have a heap. So you may not have malloc, for example. A microkernel might be implemented with malloc, or it might not be. A file system, we take it for granted. If you do programming on your regular PCs, you think a file system, everything's got to have a file system, right? If you want to save data, just write it to a file. Well, what's a file? Think about mechanisms, right? File is a sequence of bits somewhere in memory. The fact that it's on a disk means the memory is persistent, but it's just a sequence of bits somewhere in memory. Someone has to keep track of which bits correspond to which files, right? So file systems are not just sort of magically there. They're something that you may or may not provide. Security issues such as user versus kernel space are also something that may or may not be present in the operating system. Identity management. So identity management means who owns the thread that's currently executing and what permissions does that owner have. Okay. So the outline, what does a microkernel have to do? Well, it's got to set up the periodic timer interrupts. It's got to create a default thread. That's the thread that's going to start executing. Okay, and that presumably will return to that thread whenever there's no other threads to execute. Okay, so we got to have one thread that is always executing. Remember, as long as the processor is on and being provided with a clock, it will execute whatever the program counter points to and will increment the program counter. So it's got to be doing something, unless you put it into a sleep mode, which might be a reasonable thing to do in this default thread. Okay. It's got to dispatch that thread, which means, do a return from interrupt and start executing at that stack location. So what needs to be in a thread? Well, it's got to have a copy of all of the state of the processor to resume. So all the machine registers that, the values of the registers the last time the thread was suspended. The address at which to resume executing the thread, which is one of the registers. It's the program counter. The status of the thread. You have to keep track of whether it's blocked on a mutex. Okay. And you may have priorities, you may have execution times, worst case execution time estimates, and any other information that might help the scheduler make a decision about whether this thread should execute. Okay? So we'll pick up on these mechanisms in more detail next Thursday, but on Tuesday we're going to focus on projects. Okay, and so that's going to be the topic of the Tuesday discussion. So let's stop there.